Hey guys, my name's Ethan. We're going to look at the Pythagorean Theorem today, and we're also going to prove it using something from Bhaskara. So here we go. This is the Bhaskara proof of the Pythagorean Theorem. What we have here, I just took a piece of paper, a regular normal piece of paper, and I cut it out into a perfect square. Almost perfect. It's a little rough right here, but it's good enough. And just in case it is not completely perfect, but it should be, I labeled the sides, so we're going to assume everything is labeled properly and equal when it comes to the cutting out part. So moving on from that, as you can see, each side of the entire square is labeled C. So this side length right here is C, this side length right here is C, this side length right here is C, and this side length here is also C. Unfortunately, I had a lack of colors, so I had to use dotted lines and a red pen and a black pen to try and distinct things. So I'm going to try my best to walk you through what everything is. Hopefully you can keep up, but I did my best. So back to, like I said, all these lengths are C. Now the length B's are in red right here. Now the length B's, this red line right here, represents this side length B of this triangle that is formed right here. So this red line right here represents this side length B of this triangle. This red line right here represents this side length B of this triangle, and this red line right here represents this side length B of this triangle. Now for the A length, I used a dotted line with a Sharpie, so bear with me. I'm going to try and show you what it is. As you can see right here, there's a dotted line when it is labeled A right here, and that is the side length A of this triangle. So here's A for this, here's B for that triangle, and here's C. So that's forming one triangle right there. Another side length A, the dotted line right here, side length A right here, here's a side length B, and here's a C, and that is for this triangle right here. Another side length A dotted right here, A, B, C, here's one triangle, and then a dotted line right here for side length A, and so that is A, B, and C. So there's four triangles on here, and I also apologize, some of these A's look like B's, but the dotted lines are A's, red lines are B's, and the outside lengths are the C's, or the hypotenuses. Now on this square, a square has four right angles in its angles right here. So here's a right angle, here's a right angle, here's a right angle, and here's a right angle. So what I did, I drew triangles like I explained throughout this thing. I've already drawn triangles through all these, the square and the angles. So what I did, I drew a triangle. These side length A and B I drew to where this angle, when they intersect, makes a right angle, and I did that for every single one of these triangles here. So here's a right angle right here for this triangle right here. This right angle right here is for this triangle. This right angle goes to this triangle, and this right angle goes to this triangle. Now the interior angles of a triangle all add up to 180 degrees. So this angle, and this angle will all add up to 180 degrees. So let's just take this triangle right here to start off with. This angle right here, the triangle is 90 degrees, like I've shown before of how I draw it. So there's 90 of the 180 already. So now we have these two angles. Now, this angle right here, this right angle from the square entirely, because the square has four right angles, it has a line going through it from the triangle. Now this line does not bisect this right angle. If it did bisect, then both of these angles would be 45 degrees. But it is not bisecting. So to compensate for that, I labeled this angle right here theta, which means that the other angle right here has to be 90 minus theta. Because if this angle is already taking up theta, that means the remaining left over is 90 minus theta. And so if I moved on, I did it right here too. Here's a theta, 90 minus theta, and theta, 90 minus theta, and so on and so forth. So 90 degrees plus theta plus 90 minus theta will all add up to 180 degrees. And so we have four similar triangles in this entire square right here. So like I said before, we're going to be proving the Pythagorean Theorem and I'm going to show you how to do that. It will involve some cutting, so I have a pair of scissors. Like I said before, how we find the area of an entire square is the base times the height, and like I said, it's c squared, and that'll be the entire area of this square. You can also see that, like I've said before, I have a's and b's labeled, so you can see where the a squared plus b squared equals c squared Pythagorean equation is going to come into play later. So I'm just going to do a little chipping and slicing of this paper here. So I want you to watch what I do. So the first thing I'm going to do, I'm going to take this triangle right here, and I'm going to cut it out, and I'm going to shift it to another spot. Before I cut it, I want to remind you that even though I'm cutting this and putting it in different places, the area still remains constant and the same, even though it may be in a different spot. Okay? So when I move a triangle to a different spot, the area is still c squared. It doesn't matter that I moved it. So what I'm going to do, I'm going to cut out this triangle. Alright, as you can see, now I have one of my triangles. There's where it was. I'm going to shift it and put it right over here, just like that. And as you can see, I'm putting the two C's right up next to each other. Alright, so the next thing I'm going to do, I'm going to take this triangle up here, I'm going to cut it out and move it down to here. Alright, so I have it cut off, put this triangle back right here. Oh, so that triangle will go right there. I'm trying to line it up with the camera here. And this triangle, I'll fold it a little bit, will go right here. Alright, there we are. Now, like I said before, even though I did all the cutting, this weird shape that we have now made, still, the area is still c squared. Well, now your question for me is, well, how are we going to represent this as the area c squared? Well, we're going to do that by using a's and b's. The key thing to recognize is the length of this bottom right here. The length of the bottom right here. And what is the length of this bottom right here? One thing you should notice is that this triangle right here, let's take this out so you can see it a little better. You got side length C right here. Here's the side length B. And here's the side length A. So you have an A right here. Let's put it right back there. So there's A part of it. Take this triangle out right here. You can see you got side length C. You got side length A. And here's B. So let's put it back right here. So the bottom part of this shape here, this bottom length right here is going to be A plus B, because we got an A and a B. The next thing you need to realize is that this length right here is A. And you ask me, how is that A? Well, if you go back to where we shifted our triangle, this is where this triangle was in the first place. And remember, so this side length right here is A, and it fits right there. So you take this and put it back to where it was. That means this side length right here is A, and you take this triangle, this side length right here is also A. So your bottom length is A plus B. So A plus B is the bottom, and these two lengths right here of right here, and this forms a square. If you draw an imaginary line right here, you have side length A and side length A right here as well. So like I said before, this side length here is side length A, and this side length here is side length A. Well, like I also said before, you bring this imaginary line down, you form a square right here. And to make it even easier, I will draw with a pencil. Let me see if I can get a pencil that has some lead in it. Mechanical pencil props. Alright, so let's excuse the bad straight line. Let's bring this down. Let's try and line this up the best I can. So I formed an imaginary line. Now you can see it. Side length A, this is a square, and each length is side length A. So that means that the area of this little square right here is A times A, which is also A squared. Now, back to this bottom part. If each of these side length is A, if this is side length A, then we know that this part right here from this length has to be b, because the bottom, like we said before earlier in the video, is a plus b. When we did it this way, it was a plus b, but now we're flipping it around because we formed the a length right here, so the rest has to be b. So because this is b right here, and this side length right here is the b part of this triangle, that means this square that we formed right here is b times b, which is also b squared. And when you want to find the area of two shapes, you add them together. So a squared plus b squared equals c squared, like we did in the original part. Let's put it back together. Figure out how to put this back together. Turn it around for you. There we have back to our original square. That is c times c squared. So, like you've seen, that is how you prove the Pythagorean theorem. Thank you for watching.